Welcome back. Till the last module, we were looking at the long term behavior of finite state DTMCs. To give you a recap, the basic result we proved was that for ergodic unichains, the matrix P power n converges to a matrix of pi pi pi, right. Matrix where all the rows are pi as n tends to infinity. Okay. So, proving this roughly 3 steps, three main steps, right. The step 1 was considering p greater than 0, right, i.e. all p I j were greater than 0 for all I j, I comma j, right. In this case, we looked at the difference between the maximum element in any column of p power n and the minimum element, and we said that the difference between the maximum and the minimum element goes down geometrically fast as n goes to infinity, right. So, in this case we could prove p to the n goes to e pi, so this is just e pi, right, e pi geometrically fast. And this result is sometimes known as Perron's theorem. I did not mention this name last time. Okay. This result is known as Perron's theorem. Then for step 2, we considered the matrix P corresponds to ergodic DTMC. In what that means is that the entire Markov chain consists of a single aperiodic recurrent class. In this case, we took h is equal to m minus 1 squared plus 1, all right. M is the number of states, and we said that matrix P power h is strictly positive, right. This can be proven, and we applied. Then you apply Perron's theorem to P power h, which is a matrix with all strictly positive entries. Then we can show that P power mh goes to the e pi, right, pi 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 as n tends to infinity, geometrically fast in m. Then we said that the maximum entry in each column and minimum entry in each column, they are both monotonic in n, the maximum is decreasing and the minimum is increasing. Therefore, this result implied that for all n, p power n has to converge, right, by monotonicity, and the limit has to be the same as the limit along the subsequence mh, right, okay, as n tends to infinity. Oh sorry, this was m tends to infinity and this is as n tends to infinity, all right. And this result is known as Frobenius theorem, okay. This is known as Frobenius theorem. So, Frobenius theorem is a generalization of Perron's theorem, but it is also a consequence of Perron's theorem in the sense that Perron's theorem is used in proving Frobenius theorem, which is more general than Perron's theorem. Okay. Then finally, step 3, we took an ergodic unichain Remember an ergodic, so finally we want to prove that for ergodic unichains p to the n converges to e pi, right. An ergodic unichain, remember, is a finite state DTMC in which there is one recurrent class which is aperiodic plus possibly some transient states, all right. In this setting what happens is that if you start in a recurrent class, you are going to stay in the recurrent class, and step 2 Perron's theorem, Frobenius theorem would apply. If you start at a transient state, we managed to prove that we will eventually get to a recurrent state geometrically fast, right. So, we said that the probability of starting at a transient state and remaining at one of the transient states after n steps goes down geometrically fast, alright. So, you go from a transient state to a recurrent state geometrically fast, and once you get to a recurrent state, again you converge geometrically fast to pi according to Frobenius theorem, if the recurrent class is aperiodic. So, here also we could prove that, so here we again had two steps. So, if you said start at transient state, so we go to recurrent state geometrically fast, this was proven in lemma, and then once you get to a recurrent state, of course, Frobenius theorem will ensure that geometrically fast convergence to E pi, right. So, in this case it is a two step thing. So, again p to the n converges as n tends to infinity to E pi, right, where pi will consist of a bunch of zeros for all the transient states. So, these are transient states, and then so if there are r recurrent states, it will go to pi 1 through pi r, which is the Markov. So, pi 1 through pi r is the row vector, stationary distribution row vector for just the recurrent class, alright, and the transient states have 0 stationary probability. Okay. So, we did this in these 3 steps. Okay. Now, this was just a recap. In this lecture, we will look at a closer look at, we will take a closer understanding, we will get a closer understanding of how this convergence happens by looking at the eigenvalues and eigenvectors of stochastic matrices. Now, stochastic matrix is simply the transition matrix of a finite state DTMC, alright. For a stochastic matrix, all the rows sum to 1, alright, because given the bottom line being that if you are in any state, the probability of going to, if you sum over Pij over all the j starting at any I, it has to be equal to 1, because you have to go to some other state with probability 1, and therefore, sum of all rows is equal to 1, which we can write as Pe equals E, right, or rather just to be more clear. So, this can be written as Pe equals 1 E, right, where E is the column vector of all ones. All right. So, this already looks like a right eigenvalue equation, right. So, this looks like Ax is equal to lambda x, where A is just P here and E is the eigenvector and the eigenvalue is 1, right. So, this is the study that we are going to undertake now in little more detail. So, first I want to define right eigenvectors and left eigenvectors. Definition: a column vector nu is said to be a right eigenvector of P with eigenvalue lambda if P nu is equal to lambda nu, all right. So, P is a square matrix, M by M matrix, nu is a m long column vector, and if p nu equals lambda nu, you say that nu is a right eigenvector with eigenvalue lambda. Likewise, a row vector let us call it pi, right. Here I do not particularly mean that this pi is the stationary distribution, maybe I should call it pi is a specific it is a specific left eigenvector. So, I do not want to call it pi. So, a row vector, let us call it, let us say mu, right. So, this is like mu 1, mu 2 is said to be a left eigenvector of P with eigen value lambda if mu P equals lambda mu, all right. So, P is the square matrix, m by m square matrix, mu is a row, all right, and mu P equals lambda mu, then you say that mu is a left eigenvector with eigenvalue lambda. Now, note that the stationary distribution, note the stationary distribution pi satisfies, as you know, it satisfies pi p equals pi, right. So, this is a left eigenvalue equation, as you can see, with lambda equal to 1, right, which is why I did not call the row the generic row eigen the left eigenvector as pi, right. So, pi is the specific eigenvector, row eigenvector, which is a left eigenvector which satisfies pi p equals pi, namely with eigenvalue equal to 1, all right. So, generally this is an m by m matrix, right. Let lambda 1, so it will have m eigenvalues be the eigenvalues of P, okay. Please note that the eigenvalues of P do not depend on whether you are looking at the right eigenvectors or left eigenvectors, all right, because the right eigenvectors and left eigenvectors are both solved using the equation determinant. So, the right eigenvalues you will solve it using determinant p minus lambda I equal to 0, and the left eigenvectors you will solve it using determinant p transpose minus lambda I equal to 0, all right. But you know the equations, those two equations are one and the same, right, because determinant p minus lambda I and determinant p transpose minus lambda I are one and the same, right. So, when talking about eigenvalues of P, we do not have to worry about whether it is a left eigenvalue or a right eigenvalue, you will have the same set of eigenvalues. Of course, the eigenvectors will be different, right. So, what we will do is we will call nu 1, nu 2, nu m to be the right eigenvectors vectors of P corresponding to lambda 1 through lambda m, okay. These are column vectors. And we will call pi 1, pi 2, pi m to be the corresponding left eigenvectors of P. These are row vectors, all right. So, each eigenvalue lambda I is associated with the right eigenvector nu I, which is a column vector, and the left eigenvector pi I, which is a row vector, okay. To be more explicit, we are saying that P nu I is equal to lambda I nu I, all right. and for the left eigenvectors we have pi I p is equal to lambda I pi I. Okay. This is for I equals 1 2 dot 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 m, right. This is the right eigenvalue equation, this is the left eigenvalue equation for each I equals 1 to m. And also we know that for I equal to 1 we will take, for I equal to 1 we will take nu I is equal to the vector E, right, which is just the vector of all ones, and lambda 1 is equal to 1 and pi 1 is the stationary distribution pi, right. So, that we already have P E equals E and pi P equals pi. Okay. So, we are looking at I equal to 1 is the special index which I am without loss of generality taking to be lambda 1 equal to 1. So, right eigenvector is the vector of all ones and the left eigenvector is the stationary distribution pi, all right. Now, I am going to these eigen values lambda 1 through lambda m, these guys need not be distinct, okay. They could be repeated, right. However, the best intuition comes by looking at the case where all these lambda 1 through lambda m are distinct, okay. So, that is where you can get the clearest intuitive idea of what is really happening to these eigenvalues and eigenvectors, and in turn you can clearly understand how this p to the n converges to